So when we last met, we did talk about how to find critical numbers, but we did so from graphs. We didn't do it necessarily from the equations, but of course the same basic ideas are behind it. Hopefully you remember that our definition, and yes, this is in your notes already, is that critical numbers come from finding places where the derivative either equals 0 or where the derivative does not exist. So we're looking for those 2 points. So looking at this equation, it's basically a standard polynomial equation. Are there any points here where the derivative does not exist? Well, remember how we can know. We can have a derivative that does not exist if there's a hole in the graph, or if there's an asymptote. Is there a hole or an asymptote in this graph?
No.
No, because remember, those always happen because we tried to divide by 0. There's no way that equation is going to have us divide by 0. Is there going to be a corner in this graph? No. And so we know there's not a corner either because, yeah, this is a standard cubic function. And so we know there's not going to be any sharp corners. There, of course, is going to be curve in it and things like that, but not necessarily a corner where it suddenly changes direction like this sort of a thing does. So in this case, we don't even have to worry about places where it doesn't exist because we just confirmed that there are none. All right, so then the next thing we have to worry about is looking for where the derivative equals 0. All right, well, in order to do that, first up, find the derivative. So find f prime of x, please. And so when we find our derivative, we end up with 3x squared plus 4x minus 15. And we then need to look to see where does that equal 0. And so you're going to go 0 equals 3x squared plus 4x minus 15. Now, in order to solve that, we got a couple different options because it is a quadratic. You could use quadratic formula, although it's nice to save that as a last resort. It's better to factor it if we can. So check and see, is this factorable? If so, factor it. So it is factorable. You end up with 3x minus 5 times x plus 3. So then we still have to figure out what those values are for x. So set each parenthesis equals 0. So we do 3x minus 5 equals 0, add 5, divide by 3. You should get 5/3. And then we do the x plus 3 equals 0. Of course, that's going to give us -3. And so those are our two x values. That takes care of where it equals 0. Remember, we ruled out places where it doesn't exist, so those are our only two solutions. Those are the critical numbers for that equation. Having done that last one, I'd now like you to go ahead and find the critical numbers of this function, all on your own start to finish, please. All right, so when you are all done with this one, this is what your work would look like. Basically, we go straight to finding the derivative in this case because, again, as a standard polynomial equation, it has no hole or asymptote because there's no way to make it divide by 0. It's not piecewise, so there'll be no corners. And so we know the derivative will always exist. So find the derivative, set it equal to 0, solve it through, and you should get answers of 2 and -2. All right, time for another one. Let's practice this one. Please find the critical numbers of this function. And so it is factorable. The first thing you want to do is look for any common factors you can pull out. Now, the question, though, might come up, couldn't I just divide both sides by 12x? Well, kind of yes, kind of no. Technically, you could divide both sides by 12, but you can't divide both sides by the x. Because if I continue through this and finish factoring the quadratic that's in the parentheses here, it gives me x plus 1 times x plus 7. Notice what my solutions are actually going to end up being here. What can I plug in for x here that makes that equal 0? 0. If I had started by dividing both sides by 12x, I wouldn't have seen that 0 was an answer. I would have canceled that out. Remember, we are allowed to divide both sides by x only if x does not equal 0. And so this then is our final answer. Yes, you need all three of those answers. So this problem looks a little bit different, right? It's not just a straight polynomial like that. It's definitely a little bit more complicated. But our basic process is still going to be the same. I need to look for places where the derivative equals 0 or where the derivative does not exist. Now, in this particular problem, is there any place where the derivative does not exist?
Yes.
There actually will be, yeah. And now, look at y here. Think about what this equation really means. Really, x to the 1/3, that just means the cube root of x.
Oh. Yeah.
Now, for that part, are there any numbers that we cannot take the cube root of?
Yes. 0.
The cube root is 0 is 0.
Negative numbers.
The cube root of a negative number actually is a negative number, because if you cube a negative, you get a negative.
That's
only
zero.
square root.
It's square roots that we can't.
Okay.
Cubic root of 0.
And so any number that you plug into a cube root, you will be able to get an answer out, because even if it's a decimal, cube root of a positive is positive, cube root of a negative is negative, and cube root of 0 is 0. But notice what happens with the other one. X to the power of negative 2/3. The negative exponent means it's 1 over, and the 2/3 power means it's cube root of x squared. What could we plug in for x in this part of it that would make it undefined?
0.
0. Because if I plugged 0 in for x here, 0 squared, of course, is 0. Cube root of 0 is 0. But 1 divided by 0 we cannot do. So for that part, it does not exist at 0. So we've already found one of our critical numbers just by doing that.
0.
Now notice I said one of our critical numbers. We still have to go through and check, are there places where the derivative equals 0? And so for that, that means yes, you actually have to start by finding the derivative. So it's easier if we just leave it in this form. We don't even need to turn into roots for this part. So go ahead and find the derivative from that, please. So for the derivative of x to the 1/3, it's just power rule. So I'm going to multiply 1/3 by x to the power of, and then I do the 1/3 minus 1. So that's going to be a negative 2/3. Then it's minus. Now I'm going to bring down my exponent, the negative 2/3. Well, of course, minus negative, that's going to become plus. So that's going to be x. Oops, I forgot the 2/3 there. 2/3 x. And then again, subtract 1 from the exponent. So negative 2/3 minus 1 is going to be a negative 5/3. All right, we now need to solve this when it's set equal to 0. So when doing this one, it's kind of tricky, and there are some multiple methods, but I'm going to show you the method that I like the most on it. So the first thing I want to do, I'm going to go ahead and just turn this into like the radical forms. I want to make it look like the radicals. So I'm going to go 0 equals 1 over 3 times the cube root of x squared. So notice the 1/3 here, that starts me with my fraction. The negative exponent means put it in the bottom. And 2/3 power is power of 2 and cube root. Okay, then we got their plus. Nothing changed there. I have another fraction with the 2/3. The 2 is going to be by itself on top. But then I got the 3 on the bottom. And in this case, it's going to be the cube root of x to the power of 5. Now at this point, there's different things that you could try doing. But I think that the easiest way, at least by the way my brain works about it, yours might work differently, is because I have 2 fractions and it's all just equal to 0, I'm going to move one of those fractions to the other side.
Oh.
Now, it doesn't really matter which one. I'm going to go ahead and subtract the second fraction from both sides. And so that's going to give me negative 2, negative because I'm subtracting it, over 3 cube root of x to the 5th equals, now just the same fraction because this one didn't move, cube root x squared. Now, why would I do that? What advantage does this pose? Well, you'll notice now we have a proportion. Yeah, we can cross multiply here. So, cross multiply at this point. Go ahead and do that first. All right, so now that we've cross multiplied, now we can look at actually solving it. Now, notice already the whole thing feels a little bit easier. Notice you can go ahead and divide both sides by 3 at this point. Okay, so if you just did that, you might combine steps here, but if you only did that, this is what we'd be looking at. And so we got this much, but then I need to get those x's all on the same side. So I'm going to divide both sides by the cube root of x squared. Now, when we divide x's, what do I do with their exponents? When I divide x's, I subtract their exponents. Now, of course, I don't actually have any exponents here at the moment. They're the radicals, but we know what those are going to look like. We know what they represent. I know that this is 5/3, and then I'm taking away 2/3.
3/3.
Well, so that equals 3/3, which of course just equals 1. So when I divide both sides by the cube root of x squared here, it just gives me -2 equals x.
Wait.
Whoa.
Now, notice here, I just went through, I found that x equals -2, but what's our actual answers here? We're asked what are the critical numbers. The critical numbers here are x equals -2, which we just found, and 0, remember. Because remember that earlier we found that there was a point where the derivative did not exist, and that also represents a critical number. So that's your actual solution. Now, to help kind of bring home what we did and what that really looks like, let's look at the graph here. If we had graphed this function, this is what the graph of that looks like, at least on this particular interval. And you'll notice here, at our 2 spots, where x equals -2, that's that point right there. Notice my graph peaks at that point, hence the derivative was 0. So that's a local maximum, actually, as it turns out. The other point, at 0, notice what was happening at 0. That was our asymptote. Now, that's not a local maximum or minimum or anything like that, but it is a critical number, because the critical numbers tell us oftentimes where there are local maxes and mins or where there's something weird happening. So go ahead and work this one out on your own now. The first thing we do is we look for any points where the derivative won't exist. And as I'm looking at this, there's nothing right now that tells me that, because notice there's no negative exponents. So there's nothing in the original equation that tells me there will be a hole or an asymptote or anything like that happening. But it still can happen, as you'll see. But we will only be able to find that out by going ahead and finding the derivative. So we find our derivative first. So we found our derivative, then we set the derivative equal to 0, now we're solving it through. One thing to note here though, we can come back to it at the end, or we can notice it right now. I have an x to the power of -1/3. That means that we are going to be dividing by an x here, and so already we can see that there is going to be a place where this is undefined. So be aware of that as we go forward. Now, the first thing I did in the last one is I went ahead and turned it into fractions and like radical form. So go ahead and do that if you haven't yet. And so when we go ahead and put this all into radical form, this is what we're looking at. We again got a couple fractions, and since we have a couple fractions, I like to again set it up as a proportion, because proportions can be such a great way to simplify something that's otherwise really complicated. So I'm going to go ahead and move that second fraction over because it's already negative, so I can add it to both sides. And then once you have your proportion set up, cross multiply from there. So we now are at the point where we're multiplying cube root of x by cube root of x squared. Now when I do this, when I do this one, what I'm doing is I'm seeing it as we're doing x to the power of 1/3 times x to the power of 2/3. And when we multiply them, remember that means add them. So I'm going to do 1/3 plus 2/3, which of course is just 1. And so once again, awfully conveniently, it just ends up giving us an x there. Now, notice we're not done yet. I still need to go ahead and solve that out. So I divide both sides by 30. So when we do that here, we end up getting x equals either 1/5 or 0.2. Either way you say it is fine here. Now, final answer though. Where are the critical points? Well, the 1/5 is one of them, but there is another one, because I need to look back and see where would the derivative have been dne. Where would it have not have existed? In other words, what would cause me to divide by 0? Well, and you notice if I plug 0 in for x in that part, yes, the whole thing would equal 0 on the bottom, and therefore it would not exist. So 0 is also a critical number.
Okay.
So again, I want to take a look at the graph that this actually represents, because of course this is not a graph we're used to seeing. So notice here, these were my two solutions, x equals 0 and 0.2. If I graph this, this is what I'm seeing. So notice where 0 is. Notice it's not a hole or an asymptote there. 0 is actually a corner, because of some of the weirdness with the roots and all that. And 0.2, that's actually where the derivative equals 0, so you can see that it's bottoming out there. In this case, both of my critical numbers were actually local extrema. I had a local max at 0 and a local minimum at 0.2.